just polynomials. Some of them are rational functions like the one we just did. Some of them will have square roots. And so you're going to need to work through those. What do we have? T, it was this, right? Was that it? The original function? Okay. All right, so do you remember I said those shortcut rules? Yeah. Where you just look at the powers and stuff? Like if I look at the power here, you bring the power down, you would have what, 1? Then t to the 0, which would be 1. What about this?
It goes away.
It'll go away. Because we look at this as being x, sorry, not x. We look at this as being t to the 0 next to it, and you bring the 0 down, it kills it off. So maybe, I don't know, is the answer, the top is, what do we say? 1, and then the bottom is, what's the bottom if we do the same thing? 1 comes out at 2, and then minus nothing. That's not even close, is it? Our answer is -3 over the quantity 2t minus 1 cubed squared. Right. Not even close. And that's because it isn't this easy when it comes to rational functions. When you have a ratio, you have to use something called the quotient rule. So we have to talk about that. But again, that's after the test. So it's going to make life easier, but it's not going to be super easy. It's just easier. All right, shall we do another one, or what? What do y'all want to? What do y'all want to do? I see I left my mouse over there again. Damn it. See if I'm missing anything in the notes. I know I need to talk about higher order derivatives. Let's go through this.
The test, would they be like really, really hard or really, really easy to put to stuff?
I think they'll be similar to what you're going to see in your homework.
Okay.
And this problem I put on the board here is similar to something in the homework. The last one I did, just this last one. Okay, so there are other versions of when someone wants to tell you to find the derivative of a function, there's other notations, right? That's the one I'm using right now. But any of these are legitimate representations of telling someone to find the derivative of a function. And a lot of the reason why there's different notations is because the calculus was developed by two different people, and they used their own notation for what they were doing. And so we have these two notations. When you see this notation here, I've circled the three that are most commonly used here. When you see this notation, that was Leibniz. That was Gottfried Leibniz was the other father of calculus, Newton being the other. And that's the notation he used.
Can I disagree on that?
No, we can't. Because sometimes this is cleaner and easier to work with. And sometimes that makes a little more sense when you see some of the algebraic things that happen. Think about this. What Leibniz was trying to say with this is if you go back to like the curve, right? And we were trying to find the slope of the tangent line here. What Leibniz said is, look, I'm going to look at it as a secant line, which we did also, right? And he said, look, if you draw a little triangle here, this is rise over run, isn't it? And wasn't rise change in y? And wasn't run change in x? Yes? Well, Leibniz says, but what I'm going to do is I'm going to let this become infinitesimally small. It's not just change in x, it's an infinitesimal change in x, to the point where it's actually right on top of this one, infinitesimal. And so he used this notation right here, this little d in front of the y instead of the delta, to represent the differential, that limiting process of going towards it without getting there. So this is just rise over run. But get it? Yeah. Newton prime. Why? I don't know. Ask Newton. Good luck with that. I think his was a little more intuitive, or I mean, easier to understand. why he used that notation. Leibniz. Yeah. Because you can see it's simply a ratio. It's the rise over run. It's the slope of the tangent line. All right, we talked a little bit about this already. The derivative, right? If it exists at a point, then we say the function is differentiable at that point. But if it's differentiable at every point in an interval, then we say it's differentiable on the interval. So like when we have a parabola, this is differentiable everywhere. You can go to any point and there's going to be a slope of a tangent line. Because we don't have any jumps, we don't have any corners, we don't have any infinite tangents, which again I haven't shown you. Differentiability implies continuity. If you are differentiable at a point, you must be continuous there. It's impossible for it to happen without being continuous. Now, you can also state this a different way. So if f is differentiable, then f must be continuous. You can also say if f not continuous, then f not differentiable. Has anyone in here taken a logic course? Truth tables, P implies Q, that sort of thing? Okay, this is known as, this is what we call the contrapositive statement. So if you ever have a statement that says if P, then Q, then the equivalent statement would be if not P, not Q, then not P.
So that's what that means, basically?
Yeah, I did the contrapositive of this statement. So if f is differentiable, then it must be continuous. Equivalently, if f is not continuous, then f is not differentiable. So it's like negating both of these, but you have to flip the order. I'll give you a simpler example. If, this is my classic example. If you are a legal Texas citizen, then you are a legal US citizen. Agreed?
Yeah.
Can I just switch that?
No.
Can I say if US, then Texan?
Yeah.
No, it doesn't work that way. You can't flip if-then statements around like that. They don't work. But you can state it in reverse if you negate both of them. So if not US citizen, then not Texan. You still agree?
Yes.
Yes, this is the contrapositive. It's the theorem, flip the order, negate both. So this goes back to your question. What if you have a function with a hole in it? Can it be continuous there? Well, if you're not continuous, then you're not differentiable.
So then we wouldn't be able to find the derivative.
That's right, at that point, because it doesn't exist. All right. I've got about, what, 20 minutes or so? I still have a lot to talk about. I'm just gauging where I am here. I wonder if it's possible, well, you know what, before I get you to wonder, let's talk about a function that's not continuous at a point. Let's look at the absolute value function. Let's look at f of x equals the absolute value of x. And let's talk about, is f differentiable at x equals 0? Question. No. Why not?
Because there's a point.
Because there's a corner, right? If you graph the absolute value function, it looks like a V. Straight line, right? Straight line, corner, sharp corner, back up. Right? That's what it looks like. In fact, in college algebra, hopefully your instructor kind of alluded to the idea that the absolute value function is a piecewise function. It's two different functions, pasted together at 0. The first function, if you look to the right of 0, including 0. So if you're just looking from here on, what is it? What function is that? You plug in x, it spits out x. It's just the identity function. Remember the identity? It's that one. So it looks like the identity to the right of 0, including 0, because it is defined here. But to the left of 0, it's actually the identity but this way. So it's negative x, isn't it? So let's just see if that works. What's the absolute value of 5? We all know it's 5, right?
Yeah.
Okay, so first you plug in, is 5 bigger than 0?
Yes.
Yes, so the answer is 5. Okay, let's try this. Absolute value of negative 5. All right, come back over here. Is negative 5 bigger than 0? No. Is negative 5 less than 0? Yes. So plug negative 5 in right here. What's negative negative 5? Positive 5. So this would spit out 5. You see, that's what the absolute value function does. Yes? You're with me? Okay. Now, let's try and figure out what the derivative is at 0. So here's what I'm going to do. F prime at 0 equals the limit as h goes to 0 of f of 0 plus h minus f of 0 all over h. Whoa, what was that? Is that not the definition from last class with a being 0? Remember the definition from last class? F prime of a was this limit and that was a and that was a? So let's see. Let's plug 0 plus h into the function. What happens if I plug 0 plus h into the function? I have the absolute value of h, right? Minus, what's the absolute, what's the absolute value of 0? It's going to be 0, but I'll put it here. All over h, yeah? I forgot to put 0 here, sorry. Y'all still there? This is just limit h goes to 0 of absolute value of h over h. Do those h's cancel? No, they do not. You have to look at which side of h you're coming in on. So let's look at it. Let's first, remember this is a limit, and if it doesn't have plus or minus, you have to check both sides, don't you? Both ways? So let's check the left side first. I'm going to erase this. Let's check from the left. So I'm trying to figure out what this is. I should get no answer, okay? If I take the limit as h approaches 0 from the left of the absolute value of h over h, then tell me about this tiny little number you're going to plug in, right? Here's 0. You're coming in this way. You got a tiny little negative number, right? Negative 0.0001. There you go. You plug it into the top, it's going to spit that number out positive. You plug it into the bottom, it's going to spit out that number, but it's negative, right? So you have the same number, just they're off by a sign. So this would yield what? Negative 1. Because it's the same numbers, they're just off by a sign. And that corresponds to, didn't we say the slope? Look at the slope of this line. What is it? Negative 1. So the derivative is I'm coming in this way, I'm negative 1, negative 1, negative 1, right? Then I take the limit from the other side. This time, picking a number bigger, so 0.001, something like that, but it's a positive number, isn't it? Because I'm coming in from the right. When I take the absolute value of that positive number, it's going to spit out that number again, right? Positive. But the bottom this time is the same number, but it's a positive number. So we have positive over positive, which is 1 this time. Positive 1. And what does that mean for this answer right here? Does not exist. This limit does not exist. What is this limit? The derivative. The derivative does not exist. If the derivative doesn't exist, then it's not differentiable at that point. Pardon me? It's a corner. Anywhere you have a sharp corner, you're going to have a problem. Also, if you have this thing, we call this a cusp. There's a major problem here. And you can tell because look what happens. The derivative right here is what? Positive, getting really steep. And then all of a sudden when it gets to the other side, it has to flip immediately, right? Flip over to a negative. That's very different than this. Because here, it's a slow, gradual process, right? It gets to ease its way into 0 and then flip through and become negative. It's not an immediate jump from a positive slope to a negative slope. Same thing's happening here. Immediate jump from negative slope to a positive slope. All right, so there was a question that we asked, we being people, humans, is that, is there a function that I could draw without picking up my pencil? Continuous, all right? But I draw it and I pick any point and it's not differentiable. So is it possible to draw a function without picking up your pencil and it be a function that would be nowhere differentiable? Nowhere. Like the absolute value is only not differentiable here, right? Everywhere else, the derivative exists. If I pick this point, slope a tangent line there, slope a tangent line, slope a tangent line, it's only here that I can't define the tangent line. So is it possible, does there exist a function that is continuous but nowhere differentiable? It was a big problem for a long time.
Isn't it the one where it's like this? Like that one? I don't know. Like you draw like the line and then circle, line, circle in between the circles.
I don't know, I'd have to,
I forgot.
I don't think it is the one you're thinking of. Not many students have ever seen this function, which is why I'm showing it to you. So I mean, if you have, great. I don't know where you would have seen it. I'd be interested to know where you saw it. It's called the Weierstrass function, okay? And nobody here is going to be tested on it. I just wanted you to see it. But let's get an idea of what it might look like, okay? Imagine this function, right? That's just not differentiable there. I would like it to not be differentiable everywhere, so I would need it to also have maybe a corner here, right?
Would it have to have an infinite amount of corners?
Like an infinite amount of corners.
Right.
So think of like a saw blade. Those are sharp corners. Sorry, sharp. That would be not differentiable at all those, right? But let's imagine almost like a shark tooth. If you've ever seen a shark tooth, if you look at a shark tooth and you kind of zoom in, these edges are also serrated, aren't they? So if I zoom in on this, there's little serrations on there, right? And then if you zoom in on one of those, it needs to be serrated too. And then zoom in on each of those serrations and it should be serrated. Make sense? And you can zoom in infinitely. That's the Weierstrass function. And I took the time to go ahead and graph it for you. It's not in your notes, but there it is.
What does it look like?
What is the function itself? The function itself is f of x is equal to the infinite summation of this a to the n, hold on, cosine of b to the n times pi x, right there. It is an infinite summation of cosine functions. Now there are some conditions that we have to have on a and b for this to work, but if you were to be able to graph this, this is what it would look like. And it's very difficult for me to show you the serrations, but here's like the big shark teeth, and then if I try and zoom in on each one of those, and the computer's going to give up on me, okay? All right, so there I've zoomed in, and you can see there's more serrations, and if I try and zoom into those, again, my computer will give up here. It can only go so much. And at some point it just looks like nonsense. Yeah, see, you can't see them all. And there's another reason why I can't show that to you. It's because the computer can't handle an infinite number of cosine functions. It can't graph an infinite number of cosine functions. So what I'm telling it to do is like graph the first 5. If you've never seen summation, don't even worry about it.
Why is it not like the sine function instead of because the?
You could get it with the sine function. You could replace it with sine and it would do the same thing.
I was just curious.
I think I should put an asterisk next to that. I'm pretty sure it would. I haven't looked at Weierstrass in a long time, so. All right? That seems odd, but it's possible to have it's almost like, I don't know, what do you call people who shake? Tremor? It's like a person, whatever. It's a person drawing a cosine curve with this like really bad tremor thing going on. And it's like, you know, which is actually probably realistic, isn't it? I mean, even if you try and draw a cosine curve, I'm sure, you know, if you zoom in, you're going to see little, but imagine just an infinite number of little vibrations that create all these little V's everywhere. And each V has V's.
Do they use this to find like sound?
This function was actually developed, I believe, more to show it existed. Just as a pure math problem. Is there a function that satisfies being continuous? So it has to satisfy all the strict hard definitions for continuity. And simultaneously, every time you take a derivative, which is a limit, no matter where you go on there, it will never exist. So it's almost, this is what mathematicians do.
So it's basically saying, hey, I'm here, but you can't find me.
It's, well, you can't draw, but you can't write pi out either, right? But we know it's there.
Yeah.
So it's the same concept. This is a function, we can't really ever draw it correctly, but it exists, right? All right, interesting. Well, 10 minutes. See what else is in these notes. Higher order derivatives. So this again is just some notation. Hey, if we take a function and we take its derivative, right, spits out this new function, hey, why not just take that function and do it again? And it'll spit out another one. We call that the second derivative, so we put two little prime marks there. And hey, why not just do it again? And we get 3, right? That's the function, the first derivative, the second derivative, third derivative. And then at some point, it gets ridiculous to keep doing the primes, right? Because what if I wanted the 21st derivative? You wouldn't write 21 little prime marks, right? So we have to have some notation. And here's the notation we use. We usually will write the primes up to about 3. Once you go past that, you put a number in parentheses.
Are you allowed to put in parentheses prime 2?
Wait, allowed to put in parentheses what?
Is that okay if it's okay just to write f prime of 2?
F prime of 2 in the parentheses. No.
Like just write
Number 2.
I just write the number 2 instead of.
Number 2 with the parentheses around it. There you go.
Oh, without this?
No, with that.
Yeah, no, that's what, oh, okay, I'm sorry. You're saying for the second derivative specifically, could you just write that? Absolutely, that's okay. But most of the time, for the first 2 or 3, we'll just real quick primes. But please understand that the reason we put it in parentheses, I'm going to go with the higher number because it's more applicable. That would mean the 5th derivative. So you take derivative, then you repeat, then you repeat, then you 5 times, right? 5 derivatives. That is not the same as this. What is that?
They would take that function and then
Take that function
to the 5th.
to the 5th power, which means times itself 5 times, which has nothing to do with derivatives at all. So that's why we have parentheses around that little thing. So you can go forever. Sometimes it's trivial because, like if you start with a polynomial, like a cubic, you take the derivative once, you get a quadratic. You do it again, you get a linear. You take a derivative of the linear, you get a constant. Take the derivative of a constant, what do you think? 0. Why would that be? We'll talk about that next class when we meet again, not the test, of course. If I draw you a constant function, doesn't it look like this? If that's the function f, if that's a constant function, what's the slope of the tangent line everywhere? 0. So the derivative of a constant function is 0. So if you start with a polynomial and start taking successive derivatives, eventually you get to 0.
How many derivatives would you expect us to use?
A polynomial, once you get the shortcuts, I mean, you should be able to differentiate polynomials all day long.
One that like
Oh, now, you mean using the limit and all that? I mean, 3rd degree? 4th degree, maybe, but probably 3rd degree.
I was just thinking about test-wise.
Yeah, 3rd degree. All right, Leibniz notation's a little different. How am I doing here? Got a couple minutes. Leibniz notation's a little different when you go to the higher order derivatives. He writes d2y over dx, or d raised to the second y dx squared, like that. This is the way Leibniz writes it for the second derivative.
Kind of makes sense.
Does it? Why doesn't he write it just like this?
Because the y is what we're examining percent.
Yes, somebody might think this means square the what? First derivative. That's not what he wants you to do. So Leibniz says, look, so you don't confuse it with this, I'm going to offset the 2's, and that'll make you go, ah, he means second derivative.
If we were to put the 2 in parentheses, would that technically?
Which 2? Here? Like,
Nope, to the right, to the right. Last one in current.
like this?
That one.
Put this in? No. Because that parenthesis thing is reserved for Newton's notation. Yeah. Third derivative, fourth derivative, just offset the powers.
Which is a more common notation?
You see them both. You see them both. I mean, if you're in a differential equations class, you're going to see Leibniz notation a lot mixed in. I mean, it just depends. Physics, I've seen them both. Which is why we show you both, because you need to be ready to see both. Notation becomes a pretty big issue in mathematics because, you know, you get to calculus, the way we write vectors in math is usually different than the way they write vectors in physics. So there's like 3 different ways to write vectors, and so you got to have kind of like a broad spectrum so you can identify it when you see it. I believe this is the last thing. Make sure it is. Yes. So the last topic is pretty straightforward. We did discuss that if you have a position function, s of t gives you the position versus time of an object. Time, let's use d instead of s. You might think s is speed. Position versus time. If I graph this, did we talk about driving? Right? You start and then you finish at some point. This is a position function. If you take the derivative of a position function, you get the velocity function. The velocity function is equal to the derivative of the position function. So I graph this, and this would be whatever it is, okay? That's my velocity versus time. If I then apply the derivative a second time, I get the acceleration function. So the acceleration is the second derivative of the position function. So this is acceleration versus time, whatever that is. So in physics, when you have objects moving, the first 2 derivatives are important because the first one gives you velocity, the second one gives you acceleration. And I've always wanted to point out to students that if you take the y-axis here and divide by the x-axis, that's distance over time, right? Distance over time is speed. So when you look at rise over run, this is rise is distance, right? Run is time, distance over time. That slope of the tangent line, dy dx, that infinitesimal, gives you a distance over time. That's velocity. Now if you take velocity and divide it by time, you get acceleration. Because what is it? What's the acceleration of gravity? We've all taken physics. Something meters per second. Per second squared. Where does that second squared come from? Well, look, the first time I do the first derivative, I've got d over t, right? This is d over t. This is distance over time, right? Distance over time is velocity. Now, if I divide that by time again, I get acceleration. So you divide this by time again, that's where you get your time squared from. So that's all that is. Understand, kind of?
So
They're just taking the second derivative. Yeah.
that makes so much more sense.
Yeah. What would be more, I'll stop. Okay, so that's it. The test. Now I know how to get you to stay. I started making the test today. I didn't get very far with it. But like I was sharing with some other students, I'm going through the book, looking at the problems I've assigned, and I'm kind of using those as a template as to the level of difficulty and what concepts I'm going to cover. I also plan on looking at the quizzes and looking at my lectures to see the level of the problems I was doing in here. The main thing is I want to keep the level consistent with what you've seen for your homework and what you've seen on the board. But if you struggled with this, then you got a long way to go between now and Tuesday if this polynomial tripped you up. So please study hard. I'm rooting for all of you. If y'all need any help between now and Tuesday, you have my cell phone number, right? I don't know. I don't think, has anyone come to see me in my office? I've had a few students, that's it. So no one's come for help. Yeah, I mean, I'm sure you all have busy lives, but. Question?
Is today's lesson going to be the exam on Tuesday?
Yes, everything we've done, yep, to right now.
So there's no review basically, just your homework.
Yes, but it's called tough love.
He doesn't believe.
You know what tough love is? I'm trying to prepare you the best I can for where you're headed. And trust me, reviews carry people a far way without forcing them to actually become really good students. I'm trying to help you become a good student, which means you have to be able to review for something without being guided. You have to, because that's the way it's going to be when you get further on. No one's going to say, hey, this is the test just with numbers changed, or, you have to be able to take all the information in, sit down, and sift through it. So we'll see how the first test goes,
Are you taking well?
I guess not, it's too late. Yeah, so you could have skipped.
So if we done well on the quizzes, we done well on the test also?
Well, see, it's hard to gauge because this quiz to me, this would have been too easy. You know what I'm saying? So I can't say if you've done well on that, you'll do good. What I can say is if you've done the homework well and you understand the homework and you're not getting hung up on algebra, you get all your algebras tight, then you're just going to see another variety, it's a different variety of that. And, I'm going to try and keep it fair. I'm not going to try and come in here and slaughter the class with a test.
The quiz question is going to have the derivative of sine equals cosine.
What do I do with this?
What do you mean? Oh,
'Cause, yeah.
okay, yeah, so what I need to do is go back in and